In the continuation concept of the transmission lines, we will learn about the open and the short circuit lines. In the open and the short circuit lines, first we will define what is open condition and what is short condition. The diagram is very beautiful, depicting open. When a tap is left opened, the water flow is heavy. So when I close the tap, there is no water flow. So this is water analogy in terms of the words of open and close, open and short. So the same analysis can be spoken in terms of electronics and communication. When I speak about electronics, let us choose a circuit consisting of a bulb, whether the bulb glows or the bulb does not glow. When the circuit is kept open, which means that these two are not connected, then we say that this is the open condition depicted in the diagram. The bulb does not glow in this condition. When it is closed, automatically the bulb starts glowing. So these two diagrams very clearly depict the electronic representation of the word open and short. Now we'll go into the communication. When a transmission line is open circuited, what is happening? When a transmission line is short circuited, what is happening? So the short circuit in turn defines connecting a load resistor or the impedance ZL in terms of the receiving end. So now we will go into the diagrammatic analysis of what is happening in case of the impedance in case of short circuit and open circuit conditions. In this slide, we have the open circuit impedance diagram. The diagram has the x-axis representation of beta L and the y-axis representation of the reactance X. So when X versus beta L, the input reactance X of an open circuit transmission line as a function of length is depicted here. So we have the open circuit defining the load impedance ZL is made infinity. If it is short, it is equal to 0. If it is kept open, it is moving towards infinite condition. So mathematically ZL is equal to infinity. So in the general equation, we define Z of minus L, which is equal to minus Z naught of cot of beta L. So it is going to be purely reactance. That is why R plus Jx is defined by Jx only. There is no resistance, so R is made equal to 0. So J becomes equal to Jx. Z becomes equal to Jx. Then we make beta L to be very much less than 1 and again substitute the condition of cot of beta L is approximately equal to 1 by beta L, and then choose the known conditions of beta equal to omega root of LC, Z naught equal to root of L by C, thereby resulting in the impedance condition of capacitance for an open circuit condition. Likewise, for a short circuit condition, vice versa exists. We can see this very clearly in the diagram. Whether the analysis is again with respect to reactance and the transmission line length L. So we have the short circuit defined in terms of the load impedance made equal to 0. As a result of which we are making it directly equal to Jx, J is naught of tan of beta L. We again make beta L to be very much less than 1, wherein tan of beta L approximately equals beta L. Substituting all the known conditions, Z of minus L becomes J omega L, which means that it is purely inductive. So both the diagrams, a comparative analysis of open circuit and short circuit, defines a condition of capacitance and inductance very clearly. So the final condition for this characteristic impedance is defined as Z naught is equal to, with known definitions of inductance and capacitance equations derived from open and short circuit, we can finalize the condition of Z naught, the characteristic impedance, which is equal to square root of Z, which is input or transfer impedance in terms of short circuit, into multiplied by the same input impedance in terms of open circuit. So this gives a complete analysis of open and short circuit analysis in general. We'll see in the next video. Thank you.